Have you ever wondered how a single grain of rice on a chessboard could fill the entire board if doubled for each square? A fascinating question that leads us to the concept of exponential growth. In essence, exponential growth is all about multiplication. Unlike linear growth, where each step involves adding a constant, exponential growth involves multiplying by a constant. It's a growth pattern that accelerates with each step, becoming faster and faster, much like a snowball rolling down a hill, gaining speed and size as it goes. Now let's touch upon the concept of base and exponent in an exponential function. The base number is what we're multiplying, and the exponent tells us how many times to multiply it. For example, 2 to the power of 3 means 2 multiplied by itself 3 times. From population studies to financial investments, exponential growth has a wide range of real-world applications. Now that you have a basic understanding of what exponential growth is, let's delve deeper into its mathematical representation. So, how do we represent exponential growth mathematically? That's a great question. We often use a formula, y equals a times b to the x power. Here, a is the initial amount, b is the base number, and x is the exponent, which represents the number of time periods. The base number b is particularly significant. If it's greater than 1, we have exponential growth. If it's between 0 and 1, we're dealing with exponential decay. Exponential decay, you ask? It's simply the inverse of exponential growth. Think of it as a process that decreases at a rate proportional to its current value. So while exponential growth balloons outwards, exponential decay shrinks inward. But why does this matter? Because the world around us is full of examples. Population growth, radioactive decay, mortgage interest, all can be expressed using exponential functions. Understanding the formula helps us see how exponential functions are all around us. But where do we see these exponential functions in our day-to-day lives? Well, exponential functions are everywhere you look. In nature, we see them in the rapid multiplication of bacteria or the sudden bloom of algae in a pond. The number of organisms doesn't just increase, it multiplies, demonstrating exponential growth. In the world of technology, Moore's law tells us that the number of transistors on a microchip doubles approximately every 2 years. This is another classic example of exponential growth. And let's not forget about finance. The concept of compound interest, which is the cornerstone of saving and investing, is based on an exponential function. Your wealth doesn't just add up over time, it multiplies, leading to exponential growth. So the next time you see a rapidly spreading virus, a thriving population, or a soaring stock market, remember the power of exponential functions.